In the last video, we saw how a CNN scans a single image all at once, looking for spatial patterns like edges and shapes. But not all data in security comes as one snapshot. Think about a sequence of login attempts, a stream of firewall logs, or a chain of DNS requests. One event follows another, and the order tells the story. A CNN has no concept of before and after. It just sees a static picture. That's where the recurrent neural network, or RNN, comes in. An RNN reads data one step at a time, and after each step, it carries forward a memory of everything it has seen so far. As log T1 comes in, the RNN processes it and updates its memory. Then log T2 arrives, and the RNN combines it with what it remembers from T1. By the time it reaches T3, it has built up context across the whole sequence. And that context is what lets it flag a threat, like this brute force login pattern that no single log entry could reveal on its own. Why does order matter so much? Picture 4 events on a timeline: a login at 9 o'clock, another at 9:01, a third at 9:02, and then an account lockout. Individually, none of these look alarming. People mistype passwords all the time. But seen in sequence, they form a clear pattern: a brute force attempt hammering an account until it locks out. Shuffle that same set of events into random order, and the pattern disappears entirely, even though the exact same 4 things happened. A model that looks at each event in isolation, or at everything at once with no sense of sequence, will miss this completely. What we need is a system that reads events in the order they occurred and remembers the earlier ones while evaluating the later ones. That sequential memory is exactly the gap an RNN fills, connecting event 1 to event 2 to event 3, until the pattern and the alert it triggers becomes obvious. So what's actually happening inside an RNN cell? At each time step, the cell takes 2 things as input: the new data point, called xt, and its own hidden state from the previous step, its running memory. It combines these, produces an output yt, and an updated hidden state. This self loop is the defining feature of a recurrent network, and it's where the name comes from. The same cell with the same weights recurs step after step, each time folding in a little more history. That hidden state loops back into the very same cell, ready to combine with the next input when it arrives. It's a simple idea, but that one looping arrow is what gives the network memory across an entire sequence, rather than treating each input as if it existed in total isolation. It's easier to see this if we unroll that loop across time. Imagine 3 copies of the same RNN cell laid out side by side: one for T1, one for T2, one for T3. At T1, the cell takes input xt1 and with no prior memory yet produces output yt1 and a fresh hidden state. That hidden state flows sideways into the T2 cell, combining with new input xt2 to produce yt2 and an updated hidden state, which flows into T3 along with xt3. Notice these aren't 3 different networks. They're the exact same cell using the exact same shared weights, just applied repeatedly as time moves forward. That's what makes RNNs efficient. One small set of weights learns a pattern that works whether the sequence is 3 events or 300. The chain of hidden states threading through every cell is the network's growing understanding of everything that came before. This is exactly why RNNs became popular for security use cases involving sequences. Feed a stream of log lines, packet headers, or system calls into an unrolled RNN, and it processes the sequence in order, carrying context forward the whole way through. At the end, the network's final hidden state summarizes everything it just read. And that summary gets passed to a simple classifier that outputs a verdict: normal traffic or an attack in progress. This is the same idea behind intrusion detection systems that flag command and control beaconing, tools that catch slow, low and slow brute force attempts spread over hours, and malware classifiers that examine a sequence of API calls rather than judging a program from a single frozen snapshot. Sequence, not snapshot, is the whole point. RNNs aren't perfect, and it's worth knowing their biggest weakness. As the sequence gets longer, information from early time steps passes through the hidden state again and again, getting rewritten a little each step. By 10 or 100 steps down the line, the signal from that very first event has often faded almost to nothing, often called the vanishing gradient problem. Imagine a sequence that starts with malware dropped to disk at step 1, but the alert doesn't fire until step 10, after several ordinary-looking events in between. A basic RNN may simply have forgotten that critical first clue by the time it needs it most. This short memory span is the main limitation that pushed researchers to look for something better, a way to reach back and reference any earlier moment directly, instead of relying on a fading trail of hidden states. So, to recap, a CNN looks at a whole image at once, but an RNN reads data step by step, Sequence data like logs, network traffic, or user behavior, feeding into a recurring cell that carries a hidden state forward as memory, letting it recognize patterns that only emerge over time. Its main weakness is that this memory fades over long sequences. That fading memory problem is exactly what the next building block in this series was invented to solve. In the next video, we'll break down the attention mechanism, the idea that let networks stop relying on a single fading memory and instead look back directly at any earlier point in the sequence. Subscribe so you don't miss it.